Good morning, everybody. In the future, people and machines will live together. Well, let me just clarify this a little bit. What I mean is that people and autonomous machines will live together. And in fact, even more, what I mean is that people and autonomous machines are able to learn by themselves and cooperate and negotiate in large numbers, such as in huge swarms, will live together. Okay, I'm going to refine this a little bit more. What I mean is that for this to happen, people will need to trust autonomous machines that are able to learn by themselves so that we can live together. Otherwise, well, I'm going to come back to this towards the end of my talk. A little bit of introduction about myself. My name is Alessio Lomuscio. I'm a professor here in logic for multi-agent systems here at Imperial. And as Gareth was saying, I grew up in Milan in the 80s and the early 90s. And according to my parents, pretty much all I was doing at the time was playing chess and reading all the science fiction that I could actually find. This cannot be entirely true. I did manage to get a degree in electronic engineering before coming here to the UK to pursue an academic career. And what really, the topic of my research, the topic of the research we carry out in our lab is developing verification methodologies to try and reason about systems. And in particular, we want to be able to reason about systems such as that yellow submarine that you see in that slide. And why is that we want to reason about systems? Well, we want to reason about systems because we know very well in computer science that things can actually go wrong. How can things go wrong? Well, we've all experienced things going wrong with our laptops. We've all seen things going wrong with our phones. But things can go wrong in a massively more powerful way. This is something that happened right at the beginning of my PhD, 2-3 months in my PhD. This is something that many of you will remember from 1996. This is the first launch of the Ariane 5 rocket, the next generation from the Ariane 4. And unfortunately, what happened during that launch was that a fault division error happened a few seconds after takeoff. This was triggered by all the computers on board, causing a module to trigger the self-destruction of the rocket a few seconds into launch. Now, this was a long time ago. It's 1996. Here we are in 2015. What's happened in these 20 years? Well, what's happened is that the kind of technology that we had in 1996 is actually available to us every day in all the devices that we have. So the software, the good news is that the software that we've been using has become much more powerful. Perhaps the bad news is that together with that also come the faults and the bugs that come with very powerful software. Again, many of you will remember this piece of news item from about 5 years ago, the software fault of the Toyota Prius that caused millions of vehicles in the US to be recalled at an enormous cost to Toyota. We're talking about billions of dollars here of a recall for all the Prius affected with this fault. And this was a fault that affected the braking system of the car. So something that's really, really important in a car. Was this an isolated fault? Have things gone better since then in the past 5 years? Again, not quite. Only in the past couple of months, we've seen over and over the problems and the dangers of automatic software. Just a couple of months ago, the tragic accident of the new Airbus military plane that unfortunately caused a tragic loss of life to the test pilots involved. Now, what we're seeing here is automation becoming prevalent in all the devices that we're using today. But there's a next generation of physical devices and of software devices that we're beginning to see, and this is what we're talking about today, and it's autonomous systems. So again, the picture in the slide is an autonomous submarine, the one that we worked on to try and verify and give guarantees about its correctness. Well, the bad story about this submarine is that actually the first sub that was actually constructed was actually lost in the Atlantic Ocean, hundreds of meters under the surface in the Antarctica region. Okay, so think about the consequences of losing what is a one-piece device with all the sensors, all the equipment, and all the time and effort it's taken to build such a machine. Think about the complexity of insuring another machine after you lost such an expensive device. This is not the only way that problems may arise. Well, we've seen possible problems with automatic software. We're beginning to see problems with standalone autonomous machines, but this is not the only way in which problems may arise. So for those of you who've been following the progress of Google and other manufacturers in the area of autonomous vehicles, perhaps you managed to get a glimpse of a news item that came out a couple of months ago from Google, in which effectively they're reassuring everybody interested that actually the autonomous cars they're producing are doing pretty well. They're not crashing into trees or going straight at junctions. Unfortunately, the problem is, and that's how I read the news item they put out, the problem is all these humans keep crashing into us. Why are they doing this? So it is not just enough for us to design an autonomous system that actually works correctly. This autonomous system will have to live within us. And us and them will have to cooperate and understand each other so that we avoid any more possible disasters. And by the way, humans and autonomous systems is not the only area where problems may arise. Only a little later, that's only last week, we saw the problems of actually two autonomous devices, one made by Google, one made by Lexus, very nearly crashing into another. So we've seen a progression of problems here, autonomous systems standing on its own, an autonomous system standing on its own and developing a fault, their cooperation and integration between autonomous systems and humans, and now the complexities that arise from several heterogeneous autonomous systems that need to negotiate with one another to share, for example, a common space. So clearly there's dangers here. At the same time, there's also huge opportunities for all of us. We started 8:30 this morning. For me, 8:30 is a little bit of an early start. I have two children. They need to go to school. They need to go to nursery. And how great would it have been if I could put the younger one in an autonomous car so that it could be delivered to the nursery and could have walked to college with plenty of time. It's very tempting, and yet, with the risk that we have, we can clearly see the advantages, but there are also very clear risks. So the question then for us becomes, under what conditions would we prepare to trust these autonomous machines? Under what conditions would I be able to put my younger daughter onto an autonomous device with the reassurance that it would be safely delivered to the nursery and me walking to college or getting my bike to college in the reassurance that it would happen without accident? So under what conditions are we prepared to live together? Well, what I would argue is that we will need some guarantees that actually effectively the systems are largely bug-free and that can be trusted upon to do what they're supposed to do. So I'm a computer scientist, and I'm going to give you my perspective on this. So the question then becomes, how can we guarantee the behavior of an autonomous system for somebody like us in computer science? And computer science is one of the major topics that we study, certainly what we also teach at Imperial College. And one of the key techniques that we have in computer science to address this challenging question is verification. So through verification, we can give guarantees about the behavior of a system. Verification means being able to predict that the machine, how the machine will behave in all the possible circumstances, irrespective of the inputs it may be fed, irrespective of the possible functioning behavior of other machines that it's interacting with. And we could do this even before the machine is deployed. So this seems something that's very hard to do. How could we possibly do this? So how do we actually do verification? Let me give you a very concrete example through a washing machine. So a washing machine is something that is very simple for us. We understand washing machines very well. A washing machine is going to have only a handful of variables. And if you take a snapshot of all these variables at any given time, they will give you the possible state of that washing machine. Now, these states of a washing machine will evolve over time. It will start by taking in water, then heat up the water, we start spinning the drum, and so on. However, the path of all these possible states of a machine is something that we can predict very well. Why is it that we can predict it very well? The state space, all this possible configuration is very, very small. We're talking about a few hundred states. It's something that we can work out by hand or through the use of a small computer. Okay? So this is probably why, although not in these technical terms, this is probably why we rely on washing machines not to open the water while there's not to open the door while there's water in the drum, or things like this. So we trust washing machines. We're not scared of washing machines. Well, my younger daughter is actually scared of our washing machine, but that's probably because it makes an awful amount of noise. I keep telling her, sweetie, we verified this washing machine. There's nothing to worry about. Not sure it always works. But I think you got the point. It's got such a small state space. We can explore everything that may happen in a washing machine. Washing machine is 1950 technology. This is not what we're talking about today. What we're talking about today is something like this. We're talking about autonomous vehicles, for example, or in general autonomous systems. And the characteristics of these autonomous systems are very, very different from the ones of a washing machine. I can describe a washing machine, yes, by being reactive. It will do slightly different things depending on the temperature of the water that you put in. Of course, it will do different things depending on what the program you select. However, its reaction is deterministic. Every programmer will know exactly what the washing machine will do before you press the button start. That's not exactly the case for autonomous systems. Autonomous systems are capable of independent planning. They can select what to do. They can do a limited amount of reasoning. They're capable of decision making. And the more advanced autonomous systems can actually do a limited amount of learning at runtime while they're operating. Now, this is a problem for us, perhaps. And why is it a problem? Well, because if I want to verify again an autonomous system, I'm no longer talking about a few hundred of variables. I'm talking about the possible configurations of the system. It's going to be absolutely enormous now. I got this number on the slides here of 10 to the 90. 10 to the 90 is such a huge number. Imagine 10 followed by 90 zeros. The number of atoms in the universe is only 10 to the 80. So 10 to the 10 number of times the number of atoms on the universe. How could we possibly verify all the possible states and all the possible trajectories that such a machine may take during its possible computational paths? Right, this is when we turn to science, and this is when we turn to possible techniques that we may have in computer science or engineering more broadly to try and assess the complexity and the behavior of these systems so that we can trust them before they're deployed. One of the techniques that we have in computer science is called model checking. So this is a technique that the inventors of which were awarded 5 years ago the Turing Award. That's a Nobel Prize for us. And through model checking, we can very easily verify state spaces in the region of 10 to the 20. Now, 10 to the 20 is not 10 to the 90, but it's still a very big number. Again, just to give some comparisons from trivial science, the number of stars in this galaxy are about 10 to the 12. So 10 to the 20 is still a big number. The number of stars in the observable universe, I think, is about 10 to the 22. And with techniques more advanced than model checking, we can easily verify possible state spaces in the region of 10 to the 22, which is a very large number. And in fact, this is what we do at Imperial College in our lab and in other labs with our colleagues overall. We have technology through which we can input designs of systems. We can input the sort of specifications we'd like to test about the system. And our software and other model checkers will tell you whether your design is correct with respect to the specifications you want to check, or whether your design has a fault. And in case it has a fault, it will show you exactly where the fault lies and give you the trace that shows precisely the error or what might happen. So in the case of variant 5, this software or a similar software would tell you how this floating individual error may come about. So this is relatively mature technology that is no longer being taught at Imperial every year, but it's actually being used in the industry in a variety of settings. You will remember, perhaps in the 90s, the problems that Intel had with one of the first generation of the Pentium chips. And again, you'll remember the recall and the rebuilding of the silicon by Intel. You haven't seen anything like this recently. And the reason for this, or at least partly the reason for this, is that Intel, since the i7 CPU, formally verifies all the CPUs to be correct before release. Okay? So It's very unlikely, and theoretically, if the process has been done well, it's actually impossible that any of these designs actually has a fault. Okay? And it's no longer just hardware, although hardware was one of the first take-ups in the industry. Communication protocols is another example. Many communication protocols are formally verified to be correct. Formal verification has a leading role in the industry. If you've been aboard onto a Boeing 787 or an A380, you'll be pleased to know that the autopilots, large parts of the autopilot, have been formally verified. And there's other examples as well. One of them is mining. So does this mean that we can verify all the possible applications that we see today? Can we verify our phones? Unfortunately not. There's a huge number of applications that we still cannot verify. And perhaps the biggest example that we're all familiar with is in the Internet of Things, where the explosion of the devices, all heterogeneous devices and the possible combinations, puts us in a position where we cannot actually verify the composition of all these devices. So let's go back to the trust issue. How has this evolved in the past 20 years? Well, perhaps us as academics can give a little bit of a pat in the back. We have been making some progress. The progress has been taken up in the industry. And perhaps the element of risk in the adoption of new technology has actually gone down from the 90s to today. And we are now in a position where, yes, we can verify, we can say things about an enormous amount of devices that we couldn't say anything about over some years ago. The question, though, is what happens now? What happens today with the technology that we're all here to talk about? Well, what I would say is that there's certainly some known unknowns about what we're facing. So autonomous systems are becoming widespread, and this will lead to a huge space explosion. The current technology cannot deal with this. So to introduce autonomous systems, let me ask my colleague, Paul Sherry, who's president of Platypus. That's a spin-off of Carnegie Mellon University.
Hi, my name's Paul Sherry. I'm the president of Platypus. We build autonomous robotic boats for things like environmental monitoring, mapping, and generally collecting information about water. The boats are going out to all sorts of places, some of them for mapping rivers, some of them for helping with mine runoff. There's one down in Kenya right now helping do some science in rivers filled with hippopotamuses. A big difference there between an autonomous system and an automatic system is the autonomous system is understanding its environment, reasoning about what it observes in the world, and makes decisions based on that to decide what to do next. One of the fascinating things that happens with multi-robot systems and systems out in the real world is that the real world is so complicated that, and especially when you've got multiple robots working together, that the space for verification just becomes so incredibly large. It's very often we're watching 8 robots out on a lake that we've worked and written every single line of code, and we still don't know what they're doing, because what they're doing is spread out across maybe 10 square kilometers, spread out across 11 computers, is impacted by uncertain sensing, is impacted by noisy communication, as well as limited reasoning on the robots, and then occasionally bugs. And it's very hard to put down some behavior to any one of those things, even when you sit down and pore over logs for hours afterwards.
So Paul is talking about boats. He likes his boats, and I don't blame him for them. I've seen and they're incredibly terrifying. But this also relates to other classes of autonomous systems, including flying machines. And Milko will be talking about flying machines in a second. So what happens when autonomous systems, when Paul is actually successful and he starts giving us these tremendous autonomous boats to monitor our seas or our lakes? Well, there's going to be I think this curve will start building up again. We're not in the position, as Paul was saying, to verify these systems and to give full guarantees about this behavior. And in turn, this may actually mean that actually our trust in these machines will actually decrease, because we will be able to give fewer guarantees about their behavior. This is only a first step, in my mind. What's coming next is actually these boats will be teaming together in swarms. So not only will we have 3, 5, 10 boats going around, we may have very, very small boats in the thousands and thousands of boats. This will be swarm of boats where actually each individual unit is working together with its peers to do whatever that they need to do, for example, to check the temperature of the water and decide collectively where to go to take the next sample. These are acting as independent agents, but the key difficulty for us working in trying to give guarantees about this system is that we don't actually know, we don't even know how many of these systems will be deployed at runtime. So it becomes even harder for us to try and verify these systems because they are potentially unbounded. So by using current techniques, this would probably mean that actually the element of trust that we can have will further go down, and the element of risk in adopting this technology may actually go up. So what can we do about this? Well, how will we ever be able to verify these systems and provide assurances about their behavior? Well, there's a bunch of techniques that we here at Imperial College and with our colleagues elsewhere we're working on. I'm just going to mention 2 or 3 here for your benefit. One of them is called predicate abstraction. Now, in predicate abstraction, we start from the complexity of the real state space of a machine, and we do a number of abstractions where we kind of remove the details of the system, and we come up with a model of the real evolution of the system, which is more simplified until we get to the real essence of the possible behaviors. And rather than analyzing the full state space of all the system, we analyze only a model which is built automatically through a machine. And by analyzing that model, sometimes we can give guarantees about the behaviors of the system as a whole. Pretty much like abstracting a map from a picture. Now, this is a technique to address very large state spaces. There's another technique that we're working on that is called parameterized model checking, or parameterized verification, in which we want to tackle the verification of swarms. And there, the key observation that we have is that sometimes we can reason about cutoffs of a system. So if you have an enormous swarm, it just so happens sometimes that you can give guarantees about millions and millions of individuals interacting with another just by analyzing the composition of 2, 3 key elements in the system. And by analyzing the interaction of these 2, 3 elements, you can draw a conclusion about the overall behavior of any number of possible agents in the swarm. Another technique that we've actually been pioneering over the years goes under the name of epistemic verification. And here, the inspiration perhaps does come from the science fiction I was reading in my youth. Rather than verifying the variables of a system, which is what we do when we verify a washing machine. Instead here, we verify the sort of characteristics that we as humans like to think about when we're reasoning about our fellow humans. When we're thinking about humans, we're not thinking about the variables. What we're thinking about is what people know, what plans they have, what objectives they have, what laws and regulations they inhabit. And by taking these concepts on board and bringing them into the area of verification, this is what we verify when we try to verify autonomous robots. All these techniques are very explored, very actively explored in our labs here at Imperial and elsewhere. So what's going to happen when we have even more concrete results on these 3 techniques? Well, it will depend crucially on how we can actually combine these 3 techniques together. It may be that even for the case of autonomous systems and swarms, we will be able to bring down the level of risk that we have in adopting this technology. It may also happen that we're not so successful and the level of risk will actually continue going up irrespectively of our success. What I've been talking about, just to remind you for a second, is the known unknowns. Now, however, we also have a big unknown here. And this is what it is. Think about machines that can actually learn by themselves. Okay? Think about machines whose knowledge will change over time. That's relatively easy to do. But think about machines whose intentions will actually change over time. It will make up its own plans. It will actually possibly rewrite the program that it's actually running. So how can we possibly verify the behavior of a machine like this? So if I had a situation before where I wanted to verify a system with huge state spaces, perhaps infinite, that's like taking one of these leaves in this tree. It's like taking one of these leaves in this tree, which has a very large, possibly infinite state space. Now I'm talking about something completely different. I'm talking about verifying, perhaps, a whole tree whose leaves are infinite themselves, and it's got infinitely many possible branches. So it's an altogether difficult problem of even increasing difficulty. How can we possibly do this? We just don't know. Okay. But this is great. This is exactly what excites us here at Imperial and in other universities. We like tough challenges. We like to bang our heads together to try and solve very difficult scientific problems and technological problems. However challenging and interesting it is for us, though, this may also be a little risky. There may be a temptation for some of this technology to be deployed before its time, and some of this technology to become mainstream before we can give guarantees. What may happen in that case? Well, our president had just mentioned the conversation between HAL 9000 and the astronaut in the movie, and we all remember this, but we're not talking about stress pills anymore. Right now, we're talking about real medications, curing heart disease, curing a number of serious conditions, and we're halfway through thinking about assistants, autonomous assistants that actually not only administer the medication, but sometimes even prescribe the medication. So imagine it's 2030, and you wake up and hear the news that actually one of these prescriptions made an autonomous robot, perhaps in an automatic care home, has gone wrong and somebody has died. Well, it would be entirely reasonable, perhaps, for the British Medical Association to put pressure on the government to outlaw this technology simply purely on the grounds of risk analysis. But governments are not the only way in which this technology may be stopped. Again, suppose it's 15 years from today, it's 3rd of July 2030, and I like to cycle to Imperial, and suppose that I bump into a demo, and with lots of people, and I stop by and say, what's going on? And tell me there's been yet another pile-up on A406. And this has been going on for the whole week, and yet again it's caused by an autonomous car. We had enough, this has got to stop. And there is a kind of mini rebellion against autonomous systems. This is not too far ahead for us to contemplate. So should we worry about this? Well, of course, we don't want any accidents to happen, and the prudent course is always to minimize the risks. However, we should also consider that there are huge consequences of actually not adopting this technology as well. There is a lost opportunity. Clearly, autonomous systems can do dangerous jobs that humans cannot possibly do. Think of Fukushima. In Fukushima, we had workers going into the plant at huge amounts of radiation because we didn't have robots that could go in, locate a valve, and turn a valve. And this is now 2015, Japan. How is that possible? So clearly, there's benefits to society if dangerous jobs can be done by machines. Think about search and rescue missions in dangerous areas. Think about mining. There's enormous opportunities there as well. So think about all the scenarios that humans simply cannot access. So my call here is not to disregard autonomous systems, but realize that autonomous machines are coming, and really calling for all of us to devote effort to try and verify these machines and ensure they are correct before they're deployed. Verification is one scientific methodology for us to do this. Other methodologies are also possible. The point I really want to make across is that verification and showing correctness and giving guarantees about the system is something that's going to affect everybody. It's not just us in the ivory towers of academia. It's going to affect us as owners of autonomous systems. It's going to affect all the manufacturers of autonomous systems. It's going to affect the certification bodies, the regulators, everybody. Just think about the possible consequence of an accident. Where will the insurers put the blame? Which of these is going to be responsible for covering the costs? So perhaps going forward, we will see positions such as the one of verification officer in a major company, whose job really is to put a final stamp of approval to any project and guarantees that it's safe and meet the standards that they've been laid out in the company before the product actually goes out to the public, and in the interaction, of course, with the regulators. This may be a position that you will all have in the future, may come out of your IT departments, it may be something altogether different. So my vision for 2013 is for verification methodologies and formal verification technologies, such as techniques such as the model checking techniques I've alluded to become so powerful that actually these verification and correctness jobs I've alluded to actually become relatively routine. And perhaps there will be open software, open license software that we can actually download from the web, and we can input our designs, however complex, and verify their correctness, at least in terms of their initial designs. Now, I have the word here, universal. This is a little bit of a dream. We're all aware that in theoretical computer science, there are some impossibility results that tell us that we will never build the dreamlike automatic model checker that will verify all the possible designs, but there is a lot more that we can do that we're doing right now. We're just beginning to conquer the space of all the possible designs that can be verified. Okay, let me just wrap up. I said, in the future, people and machines will live together. And I think now is the time to ensure we can trust each other. Thank you.